Okay, let's talk curve sketching, which is the idea of finding a whole bunch of information about a function and then using that information to sketch the graph of that function. I won't actually get into the sketching in this lesson, but we will learn how to find the intervals where a function increases and decreases, find the intervals of concavity, and then how to use those two pieces of information to find local extrema through the first derivative test and the second derivative test. So a quick reminder, a function increases and decreases when the derivative is positive and negative, and a function is concave up and concave down when the second derivative is positive and negative. That's something you should already know. So let's look at a few examples, and in these examples, I will assume you already know how to find and simplify the derivative. I'm not going to waste time doing that. So we have this cubic function. I'm finding the intervals where a function increases and decreases. And the first thing you're going to do in all of these is find critical numbers. So I'll take this derivative, I'll set equal to 0, and we find critical numbers of -3 and 5. And how you go from here is really up to you, how you choose to organize your work. I personally prefer to use a number line that represents my derivative, and I will start by plotting my critical numbers, -3 and 5. And those two values, -3 and 5, are values that actually make my derivative equal to 0. So I like to put zeros above those two. And if those are the only zeros of my derivative, then in between those zeros, I will be always positive or always negative. And we need to determine whether each of these intervals is positive or negative. And we do that by picking a test point anywhere in that interval. I will always choose 0 if it's an option because that's a nice clean number, and then a number right of 5. And we will plug all of these into my first derivative because the first derivative is what tells you when a function increases or decreases. So I'm going to find f prime of -4. And I'm only interested in the sign. So if you want to be picky and detailed with this, you could say that f prime of -4 is 3 times. -4 plus 3 is -1. -4 minus 5 is -9. And that ends up being a positive 27. The key is that that is a positive value. And so what I'm going to do is at 4, my derivative was positive, and I personally prefer to put a buttload of plus signs on that interval so it's obvious. Then I'm going to test 0 and 6 as well. And when I plug in 0, and here's where I'm going to be a little bit lazy, 3 is always positive. I'm not worried about the 3. 0 plus 3 is positive. 0 minus 5 is negative. A positive times a negative is negative. So I'm negative here. And then I plug in 6. I get a positive times a positive, which ends up being a positive result. And now I can look at this number line, and I can tell that f is increasing on the intervals -infinity to -3, and then again from 5 to infinity because the derivative is positive. So because f prime is positive. And then I could say that f is decreasing. Boy, my writing is crap here. On the interval -3 to 5. And that is because on that interval, my derivative is negative. Okay, so I'm going to talk really quickly about the AP exam and how number lines and questions like this are read in a free response situation. And you need to know that the number line does not count at all for supporting work. That is simply an organizational tool for your eyes only, and the readers will not look at that, and they will not try to interpret your number line. And the reason for that is because the number line has never been really standardized, and there are a bunch of variations of how to do the number line, depending on the teacher's preferences. What is important is that you write down in true mathematical language how you determined whether the intervals are positive or negative. So this is the important part that is supporting my statements that the derivative is positive and the derivative is negative. Do not stop with just the number line. You have to have in writing f prime of -4 is positive, f prime of 0 is negative, f prime of 6 is positive. That's the key that will get you your full points on a free response situation. Number lines are invisible. They are beautiful organizational tools, but not graded by AP readers. So let's move on to number 2. Same question, intervals of increase, decrease. And again, I have already found and cleaned up the derivative. And there is one thing on this one you need to be aware of that did not happen on the last problem, and that is potential domain situations. And if I am ever dividing by x's, I will start by identifying where my function is undefined. And for this particular problem, it turns out that x equals 2 is a vertical asymptote. And you want to try to make note of that at the very beginning of the problem, because after you get into the calculus, you often forget to go back and think about those pre-cal and algebra 2 type concepts, and you lock into the calculus. So I found my vertical asymptote at 2. Now I get my derivative. I set equal to 0, and this derivative will equal 0 when the numerator is 0, and that happens at 0 and 4. And so now on my number line, which again is invisible, it's just an organizational tool for you, I have 3 points to plug into my number line. I have my 2 critical numbers of 0 and 4. And those 2 critical numbers actually do make my derivative equal to 0, so I like to put zeros above those. And 2, while it's not a critical number by definition, it is important enough that it needs to go on the number line as well. And at 2, we have a vertical asymptote. And I'm going to put a VA up there to remind myself that that is a vertical asymptote, not a critical number, not a zero of the derivative. It is a vertical asymptote. And we now have 4 intervals to test. I need to plug in -1. I need to plug in 1. I need to plug in 3. And I need to plug in 5. And it is much easier to determine if we have a positive or negative derivative if you plug into the fully simplified derivative or factored derivative. So again, my math language, I must write down f prime and -1, and then whether f prime and -1 is positive or negative. So f prime and -1, that will be -1 on top. -1 minus 4 is -5. And my denominator is squared, so that will always be positive. 2 negatives over a positive does result in a positive. And then I'm going to do that for 1, 3, and 5 as well. Okay, so there we see the finished number line. And now I can look at that number line and I can conclude that f is increasing on the intervals -1 to 0, and then again from 4 to infinity. And that happens because f prime was positive. And then I can say that f is decreasing on the interval 0, and we have to take a break at 2 because my function is not defined at 2. So I have to say 0 to 2, and then we resume decreasing on the interval 2 to 4, and that is because f prime is less than 0. So there are some increasing, decreasing questions. Let's talk about concavity real quick. So let's find the intervals of concavity for the following function. And this is a continuation of the function we had on the very first problem. So there's my derivative. Now we need the second derivative for intervals of concavity. So I will start by setting the second derivative equal to 0. And we found out that the second derivative equals 0 when x equals 1. And that is called a hypercritical number. Critical numbers are when the derivative equals 0. Hypercritical numbers are when the second derivative equals 0 or is undefined, as long as those numbers are in the domain of the function. And the intervals of concavity is really the exact same process as the intervals of increase and decrease. You're just using your second derivative now instead of your first derivative. So now that I have my hypercritical number of 1, I'm going to go do my number line. This number line does represent my second derivative. 1 was the only hypercritical number, and it does indeed make my second derivative equal 0. I pick a test point on the left side of 1, a test point on the right side of 1, and this one's going to be pretty quick because it's very easy to plug into 6x minus 6. F double prime of 0 would be negative. F double prime of 2 would be 6 times 2 minus 6. That's positive. And now I can say that f is concave up on the interval 1 to infinity because f double prime was positive, and f is concave down on the interval -infinity to 1, and that is because f double prime was negative. And my writing is crap there, holy cow. Just make sure that when you make any claim, so very common for the AP exam to ask, where is the function concave up, and how do you know? Justify your answer or something like that. So if I make a claim, if I say f is concave up because f double prime is positive, you have to have some work to support that claim, the explanation for why the function is concave up. And again, the work that supports that claim is not the number line. The work that supports that claim is where you found the hypercritical number and then you tested the intervals that are created by that hypercritical number. That's your supporting work for the statement that f double prime is positive and also for f double prime is negative. Remember, the number line does not count. It is not supporting work for anything. It is for your eyes only. And what I often tell my students is, if you are done, or when you are done with these problems, completely block out. Get that completely out of the way. Don't look at it. And if you still have enough supporting work left over, then you've done okay. But if you are relying on that number line as supporting evidence, then you will lose points on the AP exam. Okay, so there's intervals of concavity. I'm not going to do any more of those because it really is the same as intervals of increase and decrease. You just have the extra step of finding the second derivative after finding the first. So let's talk about the first derivative test, and that is a method or a process where you use the intervals of increase and decrease to determine if your function has a relative max or a relative min, or neither, at a critical number. And so for the first derivative test and the second derivative test, your first task will be to find critical numbers. And the way the first derivative test works is, once you find a critical number and you do the whole sign analysis with the first derivative to see where the function increases and decreases, if the derivative changes from positive to negative at your critical number, then that critical number is a relative maximum. And that makes sense because if you change from positive, if the derivative changes from positive to negative, that means your function changes from increasing to decreasing at a critical number. And so if you change from increasing to decreasing, it makes sense that that would be a max. Similarly, if your derivative changes from negative to positive, that means your function will change from decreasing to increasing. And if a function changes from decreasing to increasing at a critical number, then you would have a relative minimum at that critical number. So let's look at an example of this one, and that is this function, which is the same one we did earlier for example number 2. So I'm going to pull in our work so we don't have to recreate everything, and we will analyze the sign chart and the intervals of increase decrease of this function to determine where we have local extrema. Okay, so here is the work we had from earlier, and we already have our sign analysis done. The number line again is invisible, but we're trying to determine where we have local extrema. Do remember that every local max and local min will occur at critical numbers. So the only candidates, we can only have local extrema at 0 and at 4 if we have any at all. And so I'm looking at my number line here. And again, the number line is invisible, but it's a great organizational tool. My derivative is positive. That means my function is increasing. My derivative is negative. That means my function decreases. My derivative is negative. My function decreases again after the vertical asymptote. Then we increase. And so I have a critical number at 0. My derivative changes from positive to negative. That means that there is a local max at x equals 0. And if you want to explain how you know that, I would say because f prime changes from positive to negative at x equals 0. And I have the work to support that, not because the number line is so beautiful and sexy. It's because I have right here all of my test points that support the claim that the derivative changes from positive to negative at the critical number, which was established over here when I set the derivative equal to 0. Then we also have a local minimum at x equals 4, because at x equals 4, my derivative changed from negative to positive, because f prime changes from, and I'm going to be a little bit lazy here, negative to positive at x equals 4. And again, the number line is not supporting that. It's all of this other written work that supports it. And I'm going to keep saying that because it's very important for you to remember. Number lines don't count as work shown. So there's an example of the first derivative test. One more point I want to make here is it's very important that you label your vertical asymptote, because sometimes your derivative will change signs at the vertical asymptote. You will sometimes have a negative derivative on the left side and a positive derivative on the right side. But you need to remember that vertical asymptotes are not critical numbers, so that would not be a local extrema, even if the derivative did change signs. And that's why I like to, on my number line, indicate whether we have a vertical asymptote or a 0 or whatever other situation may be occurring at our points in question, at our critical numbers or our very important numbers. All right, so let's talk about the second derivative test. And the second derivative test name does lead to some confusion. The second derivative test still finds local extrema. The goal of the second derivative test is to find local maxes and local mins, just like the first derivative test. The difference is that for the second derivative test, we use concavity to make that distinction. The second derivative test's goal, the objective of the second derivative test, is not to find intervals of concavity. It's to use the concavity to determine if your critical numbers are local maxes or mins or neither. So the way the second derivative test works is first you find your critical numbers, just like the first derivative test. Then you plug those critical numbers into your second derivative. So if your second derivative at a critical number is positive, then that means you have a local minimum. And let's think about what that means. We have a critical number and the second derivative is positive. That means we are concave up at the critical number. If you are concave up at a critical number, then that critical number must be at the bottom of that concave up interval. Therefore, the conclusion is local minimum. Similarly, if your second derivative is negative at a critical number, that means we're concave down. And if you are concave down at the critical number, then we are looking at the point where we change from increasing to decreasing. We are looking at the local maximum. If the second derivative is equal to 0, then your second derivative test is inconclusive. And if you're looking for local extrema, then you would actually have to go back and do the first derivative test instead. And I probably should put in here, and I should have had this, if the second derivative equals 0 or if your second derivative at C is undefined. So if your second derivative is equal to 0 or undefined at the critical number, then that is inconclusive, and the first derivative test would be the route to go. So let's look at one example. I think I have one example, yes. One example of the second derivative test. And again, I have found the derivatives for you. I have not simplified them because this one's a little bit trickier to simplify. But I have my first derivative here, my second derivative here. Before I start doing the second derivative test, I have to first find the critical numbers, which means I need to factor and solve this. And so to factor this first derivative, you must take out whatever x's they have in common, and you always factor out the x with the lower exponent. So we're going to take out an x to the negative 1/3. And an optional thing to factor out that will make it a little bit cleaner, I'm going to take out the 1/3 as well. So when I do take out that 1/3, I will have a 5 and I will have a minus a 4. And then I took out the x to the negative 1/3, so the minus 4 is by itself. For the 5, there will be a single x left over. There'll be a single x left over. And the way you can kind of check that is if you multiply the x negative 1/3, negative 1/3 plus 1 is 2/3. So that would be the correct factoring for that. Now I'll, I'm not going to set equal to 0 yet. I'm going to do one more thing. When I'm solving equations equal to 0, I really don't like the negative exponent. So I'm going to rewrite this first derivative in this format, 5x minus 4 over 3 x to the 1/3, and I'm going to set that equal to 0. And we have a critical number when the top is equal to 0, and that's x equals 4/5. But also, for the first time in this problem, I have x's in the denominator, and I also notice that my derivative at 0 does not exist, but my function does. But f of 0 does equal 0. That means 0 is in the domain of the function, yet the derivative fails to exist. That means 0 and 4/3 are critical numbers. So therefore, x equals 0 and x equals 4/3 are critical numbers. Which means I'm going to take those two critical numbers, and to determine if I have a local max or a min, I plug those into my second derivative to determine if my second derivative is positive or negative. And what I'm going to do here with my second derivative, I'm going to rewrite it with positive exponents. That's going to be 10 over 9 x to the 1/3 plus 4 over 9 x to the 4/3. And I'm not factoring this one because I don't need to set it equal to 0 and solve or anything like that. I just need to plug my critical numbers in. So now that I have my second derivative rewritten with positive exponents, f double prime, I'm going to plug in 0. and I'm going to plug in 4/3, and all we care about is whether or not we get a positive or a negative result. And we run into a problem with 0 because f double prime of 0 ends up not existing, which makes sense because f prime of 0 didn't exist. So if f prime didn't exist, then f double prime will not exist either. So we will have to come back and do the first derivative test to conclude what's happening at 0. F double prime of 4/3 is kind of nice. It's ugly. You're not going to worry too much about the exact value, but I do know that if I plug in 4/3 for x, I will have all positive terms. F double prime of 4/3 will end up being positive. That means your function is concave up at that critical number. That means that f has a local min at x equals 4/3. And then that still begs the question, what in the world is happening at x equals 0? So we're going to set up and do the first derivative test for x equals 0, and I'm going to show you how that works out in just a second. Okay, so here I have my work for the first derivative test, excuse me, in green down here. So once my second derivative failed to exist, then I channeled the first derivative test. And on my number line for the first derivative test, again, my critical numbers are 0 and 4/5, and I put above those critical numbers how I got those. 4/5 actually made my derivative equal 0, so I put a 0 there. 0 made my derivative undefined. So I put DNE up there just as a reminder that it's something unique. It's not a 0 slope, it's an undefined point for the derivative. And then we plugged in -1, and I plugged in 3/5. I wanted to plug in something that plays nicely with 5x minus 4. And the derivative changed from positive to negative. Therefore, there is a maximum at 0. And so now I'm thinking, if there is a maximum but the derivative does not exist, a local maximum where the derivative does not exist would be a corner or a cusp. And so that's what's happening here. So we have a function that goes up and then it comes down sharply. So there's actually a little corner or a cusp. And then it's going to be smooth from there on out. So there is an explanation of increasing, decreasing concavity, local extrema, a lot in one video. And hopefully that made some sense to you.